Our first speaker for this afternoon is Mark Pedron from Bonn, who's going to talk to us about Strata, abelian differentials, and the Mumford Morita Miller classes.
Okay, so let me thank the organizers, and let me say that I'm really enjoying this conference so far. Yeah, let's see. So I'm unsurprisingly talking about surface bundles and then this notation for my bundle. And for me, surface bundle means that the base space is a closed oriented manifold. So and I want to put some extra structure on this. So we've already seen that there is a fiber-wise tangent bundle. So I denote this with this notation. And I want to put on each fiber an almost complex structure. So that is, put it in the morphism bundle minus the identity. So there's an almost complex structure on the fibers. And I put the almost in brackets because we know that for surfaces, basically an almost complex structure is the same as a complex structure of fibers. And the second thing I want to do is on each of the fiber we now have a complex structure, so I can talk about holomorphic one forms, so that omega be a holomorphic one form on the fibers, which is fiber-wise non-zero. Not zero. So that means that the fibers are translation surfaces. So I want to draw some pictures how this looks like. So let me start just with a simple bundle where I just have one fiber. So we have a surface, let's say genus 3, and I have one form on this. How does it look like? Generically, it will have 2g minus 2 zeros. So in this case, it will have 4 zeros. And generically, you have simple zeros. So you have something like this. This is the zero configuration of one form. Now, if we have a family, this is not true for every point. So we have to ask ourselves what happens if these kinds of zeros collide. And I will draw two pictures to illustrate what can happen. And because it's complex dimensional, I sometimes will draw things here which look one-dimensional, but they are two-dimensional, and so on. So again, here's the generic point. So we have simple zeros. Do I have another color? Yes. So, and what will happen now is that, for example, these two zeros can collide. So there will be a space down here. Is this locus? And there, with two simple zeros, and you have double zero here. So that's what's bound to happen. And then if the dimension of the base space is even larger, it could be that you have more colliding zeros. So across with the same color here, that might be the locus. This is here, this is here. Same thing here, where the other two zeros collide. So here this is a double zero, and here this is a double zero. And then over the intersection, can imagine what will happen. So we'll have two double zeros. So basically what you get combinatorically is a partition of number 2g minus 2. So in this case it's 4. And here we say it's 2 plus 1 plus. So this is this case. Or it's 2 plus 2, which is this case. And we cannot really distinguish here this branch from this branch because we have no numbering, okay? So this is one thing that can happen. Let's do another picture. So it's the same. So I'll explain the picture later. So we have here on this branch double zero here. So this was kind of uninteresting because these collisions did not interact, right? I have this collision here and this collision here, but it could be that on one branch these two zeros collide and then these. So on the intersection, which is not really an intersection, we'll have a triple zero. So yeah, let's see. Draw this. So here this is a double zero. Here this is a double zero, and then on this special point here, we'll have a triple zero. So it really looks like this. That's why I draw this picture. It's not like a clean intersection in the base, but if you compute this generically, you can see that around this point, I have two. These are coordinates on the base, so these are complex coordinates. Then and z is a coordinate on the fiber, then the one form will look like 3 plus W1z, W2 z. You can make this second term vanish by just placing your coordinate at the center of mass of these 3 zeros, and then you can see that this is like the discriminant locus. So in general, if you have higher partitions, these spaces will look like more complicated discriminant locus. Okay, so spaces. Now I want to formulate a preliminary theorem that I want to explain to you. And the point here is that I sigma the set of partitions so this means we have some finite number in the partition like this here. Then what we can do is we can look at this locus in the base. So and I would, for example, write this here as a locus 2 because we have a double zero, and then I would like this here as 3. With this here, and the focus 2, 2. And these classes here give you cohomology classes. If you look at the Poincaré dual, and the statement is classes B, sigma, and then Poincaré dual on the basis the rational stable characteristic classes. Classes of surface bundles. So I mean we know one basis for the classes, for this kind of classes, namely the monomials in the Mumford Morita Miller classes. And the statement here is that this is another one. But I think before we really understand what the statement means, I have to explain some things that are going on here. Namely, so.
The B stands for the class of M.
Oh, why did I write M? This should be B. Sorry. And Freshman notes this was M, and then I tried to be consistent with the conference and write B. So. Okay.
And what is the notation? The class is B something PD?
This is Poincaré dual. So this is a homology class, right?
No, sorry, but B brackets. What is in the brackets?
So the brackets is a partition.
In the statement of your theorem.
That's a sigma.
That's a sigma. It looks actually like a zero.
Yeah, it looks like that looks like a 0. Can you make it more
okay, I
sandy?
tried to write it.
Yeah, there we go.
So sigma is a partition. Okay, so we index over the partitions. Okay, yeah, but it will even become more precise during this talk, right? This is just so that you know where we're going. Okay, and
So is it a basis additively?
it's
When you say
it's
basis?
a rational basis.
That's another, okay.
So like the monomials in the Mumford Morita Miller classes. Okay, so some things that you might wonder about is that somehow this here depends on more than just the surface bundle, because we have this structure of J and omega. So does it really depend on this?
Perhaps you can explain the statement, because there is a genus-independent assertion, or is this?
Yes. So the implicit statement in here is that these are stable classes.
Yeah, but if you speak of basis, then you don't fix the genus, but you let the genus then sort of increase indefinitely or so.
Just add simple zeros.
Yes, so what I will do, okay, so yeah, I think it will become clearer. So what I will do is I will express to you this class in terms, so as a polynomial in the Mumford Morita Miller class. Okay, and that's also how the proof of this goes, right? You have this procedure and you calculate this, and then you see, okay, if I calculate the Poincaré rule of this in this base space, then it's just a polynomial in the Mumford Morita Miller classes.
Okay.
And that's also the proof why this is a stable class.
Okay.
I mean, a priori, nothing here is clear. Right?
Yeah, but I mean, one part of the statement is simply that these classes are stable.
Yes.
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 Okay.
So, okay, let me also say this. Stability is an issue. And then there's also the thing that, well, on the characteristic classes, we have more structure than just an edge structure, it's a ring structure. And it's also a question, can we see the ring structure in these partitions? And this is not just a nice thing to have, but this is the basis of the proof, how you prove this theorem. You first understand the ring structure, and then you see, okay, I can calculate all the products, and I can also calculate the products in the Mumford Morita Miller classes, because it's just polynomial ring. Okay, so this was just very imprecise, and now I hope I can be more precise. Let me do one example.
Wait, I don't get the statement at all. You're claiming that for every choice of a family of holomorphic one-forms, you get a class B of sigma, and that this class doesn't depend on the choice of holomorphic one-forms on the fiber bundle.
Yeah, so this here is the first question. I will come to this. And basically, no, it does not depend on the choice of holomorphic one-form of the bundle.
Well, this is obviously wrong. I mean, I can give you families where you have sections of several kinds on a surface bundle, and sometimes the locus is empty, and sometimes the locus is non-empty, where you think.
Yeah, but this is so this is a homology class, right? So this might be that the locus is not empty, but that the class is still the zero class.
Are you assuming implicitly some kind of genericity, for example?
Yeah.
Transversality.
Yeah.
And
That
also-
helps more than.
Also,
It's a kind
something
of
like
any
E
universal
has
model.
Yeah, I mean, it's not doing it for every oriented. It's somehow the universal thing is all.
Take the strata of differentials as a subvariety set MG. He's claiming these classes of the strata of differentials of a given type.
Yeah, which is the same statement that makes sense.
Okay, so I mean, you're completely right. That's what I meant with the generic thing. What we can see generically. That's I mean, yeah. Okay, so yeah, I will address this issue. Let me first do an example so that you see that it makes sense. Then if sigma is the partition where you just have, say, sigma n, and so on. But you have one higher order 0, So like this, 2 and bit 3, not like this one. And we can try to calculate this class. So, well, how do we detect the locus where we have a higher order 0? We need something technical for this, namely a jet bundle. Because the question is precisely whether the n-1 jet of the one form on the fiber vanishes. So, but I think this is a classical that I've shown. So what I'm looking at is the n-1 jet. Omega, where does this live? This is a section over total space of the cotangent bundle. So, so something is hidden here in the notation, namely this is a holomorphic jet bundle, so the dependence on the J is also in here. So, this bundle here, can you understand this? That's n-1. Well, elements in here are just like power series expansions up to order n-1. So, let's be a direct sum from k to 0 to n-1. Then you have the coefficients of the power series expansion, which lie in the bundle, and then you have this z to the n part, which you can evaluate on a tangent vector, so this also lies in e star e to the power k. And all these kinds of products are over the complex numbers, so as complex line numbers. So now here comes this genericity stuff, because I say, okay, this omega is a generic section, it's 0 locus. Right, it's like this. 0 locus is dual to the Euler class of this bundle, right? It's just an Euler class word. So if I look at the locus downstairs, so what I'm interested in is pi shriek of the Poincaré class of this. What is this? This pi shriek of the Euler class of this bundle. Now we know how to compute Euler classes. Sums become product. Products become sums. So how many factors do we have here? K plus 1. So this is K plus 1 times the Euler class of this here. So, but this is very nice, because we just have a number, and then the push down of some power of the Euler class. So this is just the definition of the Mumford Morita Miller class. What we get is n factorial kappa n-1. Okay, so
Can you explain where you use genericity and what genericity means?
yes, this is the next step. So where I use genericity here is that this formula where this is 0, that this is comparable to the Euler class. It's only true for a generic section, right? If I just take,
Why is it true at all for a generic section?
well, for a generic section of an oriented plane bundle, it's true, right? This is just the usual statement. You have an oriented plane bundle, and then you take a section that's transverse to the 0 section, and then you look at the 0 locus. That is Poincaré dual to the Euler class.
Sorry, but you're trying to take sections which are sort of smooth, only smooth in certain directions, but they're holomorphic in other directions. And you want a sort of transversality theorem for partially holomorphic sections?
I will explain to you exactly what kind of transversality is used. So this is, okay, is that okay if I answer this? It takes a bit longer, but it's also very technical, so I thought I'd start with this, and then we are motivated to go to the technical stuff. So we have to look at the space of abelian differentials. So let's first start with one surface of genus G. And then we can look at the following spaces. C of SG, that is the space of almost complex structures. So we have already seen this, or probably we have not seen this space. What you can look at is the Teichner space, which is the quotient of this by the zero component of the diffeomorphism group of this. And so I think in brackets, I will use this space because it's more natural in my opinion. Then I can look at the space A SG. This will be a space over CSG. And then we'll explain what the space is in terms of, I should say, what the fibers are. And the fibers over some element here, so some almost complex structure, is omega, where omega is a complex one form on SG, which is holomorphic with respect to J. And it's not zero. So not completely zero. Okay, so what do we know about the spaces? Well, first we know that the space is contractible. And secondly, you know, in this space, well, this is almost a vector bundle, right? Because if you fix J, then the space of holomorphic one-bonds is just a complex G-dimensional vector bundle. If I take out the zero section, this is homotopically the same as a sphere bundle. So I will just write here that pi A is a 2G minus 1 sphere bundle. Okay. So this is just for one surface. Now we're looking at families of surfaces, but we can take the same definitions. So right, CE, and what is this?
Sorry.
Shut it off. I'm sorry.
Okay, so this will now be a bundle over the base, and the fibers of this are then the almost complex structures on the fibers. So this bundle of almost complex structures on the fibers. So in such a way that if I look at the sections, would be so in some way the smooth sections, of course, of E. An element in there is a family of complex structures on the fibers. So, C structures. And then
what is C of E to be kind of a bundle? I mean, your notation is hilarious, but what is the fiber of C of E to be? What kind of object is the fiber?
The fiber over the point B.
Yes.
Is
C of the surface.
C of E over point B.
You're patching Teichner spaces or spaces of complex structures together.
Yes.
You're looking at the Hodge bundle, right?
No, the Hodge bundle is A.
So,
I mean, his notation is like let K be a vector space over.
So the topology on the space this is a locally trivial bundle, E over B, right? So you take also locally the product topology on the space. So locally, if you have if you have the fibers and then you trivialize E, then you can put the product structure and then you just glue it together by the inducements. Okay. So, and
can you move the board up, please, so you're not writing in the shadow?
Yeah, sure.
The dark.
Thank you. Okay. And you can also look at this bundle, and this bundle is then the bundle of abelian fiberwise abelian differentials. Okay.
So over each point in B, you have now put an infinite dimensional space, C of E, and
Yes.
over that you've put an additional vector, almost a sphere bundle of rank 2G minus 1.
Yeah, so what we have here with maps is this first and forget my map C of E, and both of these are bundles over B. Okay, and then the fibers is exactly what's on top. Okay, so, and now the point is that fiber-wise we have this contractibility and we have local triviality. So the statements from here translate to the following statements, and if you look at the space of sections here, it's still contractible. So, here, and well, what is with the sections in here? Somehow the connectivity of the space depends on the space, so on the connectivity of the fiber and on the base space.
How come that the space of sections over B is contractible disregarding the topology on B?
Because this is locally a product where the fiber is contractible.
So what? Being locally a product is
Space
a
of
basic-
sections, any fiber bundle
Of
is contractible.
a bundle with contractible
Unless
fibers.
B is linear.
Should be contractible.
So B is manifold here, right? So
But I have a feeling that isn't it easier actually if you take just the universal model, meaning you take the Hodge bundle of the moduli space of curves, you take in there the strata, you close them off. I mean the projection map, it uses an isomorphism and cohomology, right? Hodge bundle is the same cohomology as the base. And these cycles, they live upstairs.
yeah,
You close them up, and then they define cohomology classes in the degree of their real codimension.
yeah, I agree. That's the same. So it leads to the same classes, but the point is that well, you have to understand the singularities, and this orbifold structure makes it really complicated to understand the singularities in here. So I really want to use methods of differential topology for actual surface bundles and not just for some cycles in this modular space. Because on the modular space you do not really have this surface bundle, and you also do not really have this local picture. I mean, we can talk about orbifolds, that's also okay. I'm fine if you just go to the
You
orbifold.
take this three-level structure, if you like. Well, I mean, that's innocent, I would say.
Well, I mean,
I mean, a finite group is better than diff.
so I think we have to go on, right?
The
Because
whole
we have
diff, not just the mapping cloud group, is taking the whole diff.
Okay, so let me just say that this is now contractible, and then if you look at the space of sections of this bundle, then you can see that this is 2G minus 2 minus M connected. That's just a complication. So, and what this tells you is that if the fiber genus is large compared to the base manifold dimension, then you get a section in here, and if it's even a little bit larger, then all the sections are homotopic to each other, so it does not depend. In the case where this is not path connected, so in the case where 2G minus 2 minus M is smaller than 0, then well, you can ask what is the definition in this case? Well, I'm now cheating because I say, okay, in this case, I just set this class to be 0. So in this case, I say, okay, the class B of something which is not really defined. 0. Why can I do this? There's a theorem of Loyenka which tells you that in this range, all polynomials in the kappa classes on the modular space, or also in this ring of version stable class, are actually 0. So this is a good definition in this case. So this is consistent with volume as the cover classes.
Except that I'm telling my students not to have 0 elements in the basis.
You said they form a basis.
It makes a basis of the characteristic classes.
Yes.
In some sense, it's for all B.
Yeah, so, right, so.
It's for all B.
I think it's okay.
You can choose the universal B. He's thinking, he's giving a description of the ring of characteristic classes, so it's not specifying one single B.
Okay, so I think I skipped one computation. No, I tried to summarize this. Discussion. So the summary is that I have sigma in the partitions. Yeah, these are the symmetric partitions of some number. Say 2g minus 2. B is the manifold dimension m. Then for 2g minus 2 minus n greater or equal to 0, that's when in this case the space is path connected, the class H of sigma in the cohomology ring of the base, say H of sigma and E of just because of the bundle, where H of sigma E is the Poincaré dual V sigma, is well defined and independent of the choice. Of J and Y. Right? Because it's path connected, so if you have two, then you can just go from one to the other, and then you will see that you get cobordism in the base. Yeah, so we have these classes. And
I have a little question, maybe I missed something. These B sigma, they are not exactly manifolds, they're not exactly submanifolds, right? They are pseudo-manifolds.
yeah, so what they are is, so I think the most elegant way to see that they define classes is to recognize that they are stratifolds, where they are stratified with strata which all have even codimension. So I don't know if you have something like this.
Yeah, algebraic varieties, pooled back, right? I mean,
Well,
algebraic
except
variety.
B isn't algebraic.
Yeah, except
No, but they're pooled, I mean, the
They're pulled back
universal
from
example is algebraic.
Yeah, okay, I think it's nice that we have algebraic people and topology people and we have different definitions of the same objects.
Algebraic cycles.
Yeah. So, okay, let me try to formulate the actual theorem. So, the theorem is that if you look at the vector space, on the partition. So we take the vector space and as basis we take the partition of the numbers 2g minus 2. Then this has a structure of an associative algebra. Such that there is, so okay, let me say something more about the structure of the algebra with generators sigma n, which are just n plus 1 and so on partitions, such that there is homomorphism to the ring of characteristic classes. Okay, and let me, I mean, for you, I will write this notation. Okay, so, and what does homomorphism do? I mean, well, we need some here, and that it sends partition to the class, which is defined in this way. H of sigma, this is a characteristic class of surface bundles, and it sends.
Can you again move out of the shadow? Thank you.
So then it sends this class n to n factorial kappa n minus 1. So I think I do not have that much time to talk about how we prove this theorem now. So one thing you have seen, namely that we can send these generators to these generators. The other part is that you have to understand the product structure on this ring, which amounts to understanding the intersections, which are quite singular, and then seeing that you can find this algebraic structure. And okay, once you have this theorem, the other theorem follows, right? Because you can stabilize this. On this side, you just add simple zeros to the partition. On the okay, I have not told you what the algebra structure is, but then you have a stabilization map on this side also. You have here a stabilization map, and in the end, what you get. So put this also in the theorem. If you take the limit, that's actually right, the limit of the co-limit, g goes to infinity of this algebra. As graded algebra. Then this is polynomial algebra. Okay, and now we do something like this for polynomial algebra, which is generated in the pattern. Which is generated in this partitions. And then if you have this polynomial algebra, and on this side you have the polynomial algebra, and you see that generators are sent to generators, then you recover the theorem that I stated in the beginning. Now I have 6 minutes, so I think I will tell you a little bit about, so because there was also complaints what this means to be generic and what are actually the conditions. I will try to clarify that. So with this basis on this blackboard, and I mean from the questions about the topology, so well you could see that it's actually not so nice to work with this infinite dimensional spaces. I did this because it's more natural in this context, but we have this finite dimensional replacements, for example the Teichmüller space, which is homotopically the same. So you can look, so the model setting, the space T of B, which is just, so this is the same as the fiber-wise Teichmüller space. Where you map out on each fiber the action of the diffeomorphism group. So what does this mean? That if you have a section in here in this Teichmüller space, this is the same as a section in this space of complex structures. One of the sections of the fiber-wise diffeomorphism groups which are homotopically the identity.
No. Sheath associated with that pre-sheath.
Yes, okay, that's correct. I think in the, I don't know if you need this in a differential setting, but what you can also do is you can take the space of abelian differentials and work out this group. Let me write this symbolically as this, and then also means what you said. I think here you really need to mod out this, you need to sheafify because you only take local quotients because it's not contractible. Okay, so this is Miller space. Of abelian differentials. And in here, this is now a finite dimensional bundle. In here, you have, so this H of E. In here, you have a stratification. And the stratification comes exactly from the spaces where the zeros of the one form have a specific pattern. So this is stratified by something that I will call in this context strata of abelian differentials. I mean, probably you would like to say, okay, that's not the correct definition. We also want to mod out the mapping class group. Yeah, okay, so in the over the modular spaces strata are, we also mod out the mapping class group, but in this, this definition. Prescribed zero partition. And these are submanifolds. So the open strata are submanifolds. And you can use in this setting the transversality theorem to say, okay, I want to find a section of the space. This is the data that we use, the omega and the j. I want to find a section of this space which is transversal to the strata. So omega generic is defined to be transverse to the strata. And that you can always arrange because it's just the usual transversality theorem for differential topology. And in that case, also the other equation goes through. Yeah, okay, I think in the interest of time, I will not start another chapter and stop.
Are there any questions?
Just to be clear, are you claiming that you have a formula for the fundamental class of the strata in the strata of translation surfaces?
Yes. So
do you have an explicit formula? I don't think you wrote a formula on the board. You said there exists one.
No, so there I have a formula for the multiplication of the strata.
Yes.
So the point is that if you look at a stratum, let's say for example it starts with numbers,
yes.
Then we take this number, you will get kappa 2 for this, so we use some factor, I don't care about factors. For this number, you get a kappa 1, this is a leading term. Here you get terms of lower order. This means lower order in the polynomial degree, not the cohomological degree.
Yes. Do you have a formula for those?
So for these,
yes.
I have a formula for the product. And what you need, if you want to go from one basis to the other, is that you calculate the product and then you get these terms of lower order, and then inductively you try to erase them by finding products on the other side which manage these, and then you have an inductive computation.
Is this product formula, is that in the literature? I mean, it is on that vector space, right? You turn that into an algebra.
Yeah.
That's what the theorem says. So this algebra structure, is that known?
I think so far it's not known. So at least I haven't found it anywhere, and I compute it. Yeah, and so okay. Yeah.
Sorry, I have one more question though. Can you tell us how your formula compares to Gabriel Mandela's formula for the classes of strata?
I have no idea how this formula looks.
He has a formula in terms of the psi classes, I believe.
Ah,
Is
yeah,
his
okay,
formula.
yeah.
Is it yours, how does yours
So,
differ from his?
so I haven't, so what you mean is that there's a, if you look at the modular space where you mark the zeros, right? And then you have the additional classes, the psi classes on that. Then there's this formula. That's correct. So theoretically, a way to compute this formula is you use this, and then you try to project to the modular space without the ends by pushing down the psi classes and calculating them here. I haven't tried it. So just 2 days ago, I tried this with David together to get some formulas out of this and to compare it, but we haven't managed so far.
Any other questions? Oh, yes.
If you fix this GS, right, and so you look at your construction, so you get actually the whole sub-algebra generated by the tautological classes. And of course, well, we have these Faber conjectures, some of them are known, some of them aren't. Do you recover some of that, or do you sort of, does it contribute to this?
Yeah, so okay, let me just answer this. Okay, so you mean that we already know relations in this case, namely the Faber-Sage relations, right, between the kappa classes, and obviously this theorem also gives you relations because this is finite dimensional, so you get some relations. I guess that these relations come from the Faber-Sage relations because the construction of...
No, I'm asking something similar. For instance, we know that these monomials are zero as of a certain degree, right? If you have a monomial of degree g minus 1 or higher, then it's zero. So does that perhaps...
You do not get this in the same grade. So you also have a top element here, but this is too much. So you do not get all the relations.
No, but for instance, you take the top element and can you see it actually on the left-hand side somehow that is homological zero?
No, you cannot. For all elements that are larger, you can see that they're zero, but not for the top element. It's does not follow on this computation.
You don't see it because the bottom strata is the locus of hyperbolic curve. If you take a partition consisting of single integer 2 to minus 2, that includes exactly the locus of hyperbolic curves. So your work to show that it's not zero. So from this report, you can see whether it's zero or not.
Okay.
Plus the other strata, which you also have to treat.
We don't go that deep because as these are the minimal dimension of the strata.
Any other questions? Okay, let's thank Mark again.